Hello everyone. First of all, I'd like to thank the organizers for inviting me to give this talk. It's a nice opportunity to give a talk in a conference, even though it's hard for me to travel all the way from Chile with a little kid. I can't do much traveling for a while. And I wanted to turn the spotlight to a few alternative methods that people have developed for measuring primordial non-Gaussianity. I'll talk about my own work, but also about other people's work. Though this won't be a review talk, it will be biased on the methods that interest me, which they interest me because I think it's interesting, because I think I can contribute a bit. So first I'll talk about what is primordial non-Gaussianity, then I'll talk about what are the traditional methods to constrain primordial non-Gaussianity, and then I'll introduce a couple of methods or classes of methods. The first one, exploiting the simplicity of the squeeze limit of the bispectrum, the almost triviality of the squeeze limit on the bispectrum, which tells us how a long wavelength perturbation modulates short wavelength observables. And then I'll talk about topological data analysis techniques applied on the point cloud of halos or galaxies. So what's primordial non-Gaussianity? So the community has done much progress understanding the universe in the last few decades, exploiting the two-point correlation function. And we wonder whether we miss cosmological information hiding in more complicated statistics. Basically, anything going beyond the two-point correlation function is non-Gaussianity. Here we will be interested in primordial non-Gaussianity, meaning a primordial, for example, a primordial three-point correlation function. So I correlate three primordial metric fluctuations in this case. We know that due to translational invariance, this three-point correlation function has to be proportional to Dirac delta, which means that the three Fourier modes have to form a closed triangle. Whatever is left, I call the bispectrum. I will use bispectrum and three-point function interchangeably. I know that some people prefer to reserve three-point function to the position space and bispectrum for Fourier space. I will always talk in Fourier space, but I'll call it bispectrum and three-point function. If I assume scale invariance, I can factor one of these scales such that I can plot this bispectrum in a two-dimensional plot. And since this is symmetric under the exchange of K1, K2, K3, it all reduces to this triangular region in this plot. If you don't assume scale invariance, you can do some fancy 3D plots that people like, but for my purposes, it's enough to talk about this two-dimensional thing. And we will be talking about some, just to introduce some jargon that I'll be using. So in this region of the plot, we will call it the squeezed limit or the squeezed region of the plot. This is because it corresponds to this triangle between the momenta in which one of the modes, which is squeezed in the sense one of the modes, is much smaller than the other two. In this specific diagram, it's K3. Anything which is not squeezed, so anything away from this limit, we will call it quote unquote equilateral, meaning, so equilateral will mean that there is no hierarchy between the momenta. Okay, so how can primordial non-Gaussianity be observed? You can either try to observe it directly by measuring the three-point function of the fluctuations, say, for example, temperature fluctuations in the CMB, and this is how CMB constraints that I'll quote later are put. But my talk will focus on the large-scale structure. So if you take your galaxy positions, you can define a galaxy number density contrast field in this way. And this galaxy number density contrast will somewhat trace the dark matter density contrast. And dark matter density contrast itself traces the gravitational potential, meaning the metric fluctuations sourced primordially during inflation, through Newtonian scales through Poisson's equation. So there's a k squared in Fourier space in front. And you can try to measure directly the galaxy number density contrast correlation 3-point correlation function, which of course is sensitive to the potential 3-point function, the primordial potential 3-point function. Or you can try to measure, you can also measure a primordial 3-point function through the 2-point function of galaxy numbers, because galaxy or halo formation is a very nonlinear process that depends on all correlation functions. And we will see more explicitly how this comes about in a second. So in order to understand how constraints are put, let's consider a phenomenological model in which the metric fluctuation, or gravitational potential, if you will, is given by a Gaussian field plus something proportional to the Gaussian field squared. Now, if you compute a bispectrum from this, so you take the 3-point function of this theta, assuming this is Gaussian, you get this with some power spectrum amplitude. And if you plot it, this is a shape that diverges in the squeeze limit. It's non-zero everywhere, but it has a divergence as one of the modes goes to 0. Then, if you want to compare this phenomenological model with your data, what you can do is, if you have some favorite model of inflation, you can compute how much your primordial 3-point function, I call f the bispectrum in this slide, you can compute how much your primordial 3-point function overlaps with this model, for example, using some cosine that computes similarity between the shapes. And so this is how constraints are put, and data is analyzed for a few simple shapes that have nice numerical properties. One of them is this one. In particular, this local type of shape is the one has this divergence, which is characteristic. We will see that it's a smoking gun for a multifield model of inflation. So by putting constraints on local non-Gaussianity, you are, in a sense, putting constraints on multifield inflation, because you're using a template which has a divergence that you expect from multifield inflation. But you can also probe single field models, and there are a couple of other simple templates with nice numerical properties that are used to put constraints on data, which are the equilateral template, and it's called that way because it goes to 0 in the squeeze limit, and it peaks. It has a maximum in the equilateral, for equilateral configurations where all the momenta are equal, or the orthogonal shape. It's called orthogonal because it's orthogonal in this cosine that I showed you before to the other two shapes, and it's non-zero everywhere, and it also assumes no hierarchy. There is no divergence in the squeeze limit, as you can see, and there is no hierarchy. It doesn't assume a hierarchy between the momenta. Now, the current constraints are put by using the cosmic microwave background, but the future is the large-scale structure. The near future is the large-scale structure. In the next few years, we will see data coming from several experiments: the Euclid satellite, the LSST survey, DESI, and the spheric satellite that will be launched. But what can we learn from the bispectrum? We can learn a lot of fundamental physics. For example, it has been shown in this series of papers that if you have a single field model of inflation, by single field I mean the following. Of course, there can be many fields present during inflation, but only a few can contribute to primordial fluctuations, and they have to have a mass much smaller than the characteristic energy scale of inflation, which is the Hubble scale. So you have a single field contributing to the primordial fluctuations. It has been shown in the series of papers that if you assume scale invariance, the primordial bispectrum has to have a divergence going like 1 over q. It cannot have a stronger divergence, and this is what's shown here. And moreover, if you don't assume scale invariance, there will be a stronger divergence, but the coefficient of the stronger divergence is completely controlled by symmetry, because it can be shown that it's a trivial effect, a trivial geometrical effect, so completely fixed by a change of reference frame. So so there cannot be a non-trivial stronger divergence than this if inflation is single field. If inflation is multifield, we know from explicit computations. So if you have several fields which have an energy scale much smaller than h, this is like a mass spectrum where I'm plotting with lines the masses of the different fields. If you have several fields which are with a mass much smaller than the characteristic energy scale, you can have a stronger divergence, and you can even have intermediate behaviors if you have fields which have masses of the order of h. And I took this figure from this paper here. Moreover, you can also learn something more. If you include additional fields with non-zero spin, in the squeeze limit, not only do you have a divergence, but this divergence has a characteristic angular dependence, where the angle is the angle between the momentum going to zero and the other momenta. That depends on the spin. So you can even try to constrain the spin with this. So you can learn a lot about multifield. You can have a hint on the mass of these fields and the spins, but you can also learn more even in the single field case. So if inflation has a single field, is responsible for fluctuations, you can write down an effective Lagrangian and the coefficients of the cubic terms, this one, which, well, I should have highlighted this one, and this, so this coefficient is fixed by the quadratic term, by the speed of sound, and this one is free. And you can hope to constrain these two by observing primordial non-Gaussianity, because these two induce 3-point functions. In particular, we also have two shapes that can be used to constrain these two coefficients. The equilateral and orthogonal phenomenological shapes can be used, since they are independent, they can be used to constrain independently these two coefficients, and this has been done for the CMB and the LSS in the literature. So by observing the equilateral and orthogonal non-Gaussianities, we can learn about the effective Lagrangian of single field inflation, if inflation is single field. Moreover, even more interesting in my opinion, is that if there is copious particle production during inflation, this implies generically an equilateral kind of non-Gaussianity of order 1. By equilateral, I mean no hierarchy between the momenta. Very generically implies non-Gaussianity of order 1. Why is this interesting? Because we, in most models, assume that the inflaton vacuum fluctuations are responsible for creating the fluctuations we observe in the CMB or the large-scale structure, but they could also be thermal fluctuations in models with copious particle production, so-called warm inflation models, or even if scalar fluctuations are generated by the vacuum, maybe some violent particle production can produce gravity waves, but this, which could be observed as B modes in the CMB, but they also very generically produce a large equilateral non-Gaussianity. So by constraining equilateral non-Gaussianity, we are also constraining those possibilities. So we are figuring out whether fluctuations are sourced by the vacuum or other processes, which I think is interesting. But how can this be observed? So I already said, you can try to observe it directly through the 3-point functions, but you can also try to observe the 2-point function. And I want to give some detail on this, because I think it's still the leading method to constrain, it will be the leading method to constrain primordial non-Gaussianity going forward. So the idea put forward in this series of papers by these people is that imagine you have a local type of non-Gaussianity, so your gravitational potential is given by this, and you study how objects form. So of course your field is a sum of Fourier modes. So when you cross some threshold or something, you form a galaxy. So let's consider the simplistic model. If FNL is positive, there will be an enhancement of modes which are already on top of the long wavelength mode. If there is if FNL is negative, there is a suppression. So this leads to a biasing of your object formation, a biasing which depends on this coupling. Another way to see it is if you take your galaxy 2-point function, and if there is a correlation between, if the gravitational potential has an effect on your halo density, then this 2-point function will have a term like this. So we'll have a term where you correlate the gravitational potential with the halo density. And if you write your gravitational potentials in terms of your halo density, you have to put something that goes like 1 over k squared. So you have a bias that goes like 1 over k squared. This in the literature, roughly like 1 over k squared. This in the literature is called sometimes a scale-dependent bias, which is how I will call it, just to give it a name throughout this talk. And moreover, this correlation between the gravitational potential and the halo density field cannot be induced by anything else than primordial non-Gaussianity or some very strange violent breaking of the equivalence principle. So let me argue this because it will be important also for the methods that I will explain later. So let me argue that there is no coupling, which is not primordial non-Gaussianity, between a large wavelength gravitational potential and small scale physics. And for that, consider a very nonlinear object, like very complicated, like a galaxy, on top of a gravitational potential. We know Newtonianly, I will make the argument Newtonian, it can also be done relativistically, as is done in this paper here. So you know that you can set this long wavelength fluctuation to 0 simply by changing the 0 of the potential. So trivially, we know that a constant gravitational potential cannot have an effect on short wavelength physics. So a very long wavelength potential, which you can approximate as a constant, should not correlate with your halo number density, because it shouldn't affect halo formation. And the same can be said also for the gradient of the potential, because if the gradient of the potential is a constant gravitational force, which of course you can set to 0 by going to Einstein's elevator. So it's a trivial effect given just by a change of reference frame. So there is no dynamical correlation between a gradient of the potential and the halo number density. It's a trivial change of reference frame. Of course, so this means that you cannot have 1 over k squared. You cannot even have 1 over k behavior, or rather the 1 over k behavior is trivial. So that this cannot be induced by astrophysical phenomena, because they have to satisfy this simple analysis. They have to satisfy the equivalence principle. So this should be true for any very nonlinear object. So what are current constraints on non-Gaussianity? So these are the CMB constraints, and the goal, the holy grail of this effort would be to constrain non-Gaussianity to order 1. That's because for equilateral kind of non-Gaussianity, order 1 is generically what you expect from having, for example, copious particle per production. If you constrain this kind of non-Gaussianity to be smaller than 1, you may be able to rule out those kind of models. And for local non-Gaussianity, 1 is a nice number to give. I don't think there's a strong motivation to say 1, but one can argue hand-wavily that it's kind of the natural number that you expect in a multifield inflation model. Now let's look at the latest large-scale structure constraints. And you can see that we are still far from order 1. Even for local non-Gaussianity, this is 1 sigma constraint. So we are at 1 sigma, we are 1 order of magnitude away from what we would like to, where we would like to go. At 2, 3 sigma, we are even 2 orders of magnitude away from where we would like to be, even for local non-Gaussianity. Now let's look at current large-scale structure constraints. They are not yet competitive with CMB constraints. As you can see, error bars are roughly an order of magnitude larger, but things are expected to improve in the near future with the surveys I showed you. But let's look at a few forecasts. So these people here forecast that a Euclid-like survey will be already competitive with the CMB, which is amazing. While LSST-inspired, that's how they call it, survey or SphereX, will be able to put constraints on FNL local of order 1. Most of the constraints can be order 1 only using the scale-dependent bias that I talked about. The bispectrum greatly improves constraints. In particular, it can break degeneracies because a disadvantage of the scale-dependent bias is that we don't know what the coefficient here in front of this correlation is. You can sort of kind of model it. It's not clear how well you can do with these models. But an agnostic analysis would leave this coefficient free. So it's hard to relate the value of this coefficient with FNL. However, observing a behavior like this, even though it doesn't give you a number for FNL, would be a smoking gun for multifield inflation immediately. So it's interesting in itself. Okay, more recent and also more recent constraints that put a bit more effects into their analysis, making them slightly more realistic. Give FNL errors on FNL local of order 0.8 for mega mapper kind of surveys, and on FNL, interestingly, for FNL equilateral, mega mapper kind of surveys will be competitive with CMB constraints. It's slightly depressing in the sense that it means that the best we can do with large-scale structure for equilateral non-Gaussianity is get at the same level as the CMB. However, so it means traditional methods would only be able to get here. For the local non-Gaussianity, there will be an improvement of at least an order of magnitude with respect to the CMB. So those are traditional methods. Now I want to talk about alternative methods that people have been working on and that I've also helped in developing a bit. So let me talk about the one that I've worked the least on up to now, which are squeeze limit methods. These methods exploit the fact that the squeeze limit if we want to constrain a primordial non-Gaussianity and we want to constrain how it diverges in the squeeze limit, the more direct approach, also the approach that is the cleanest physically, is to directly look at the squeeze limit, because a correlation in the squeeze limit would be a smoking gun for primordial non-Gaussianity. While if you analyze the entire shape, you are not sure whether you're getting a contamination from other regions which are more model dependent. I mean, you can always write multifield models that give you something or another in regions away from the squeeze limit. So you want these methods focus on the divergence on the squeeze limit. Also, the scale dependent bias focuses on that divergence. So it's also a clean method to detect multifield inflation. But these methods, what they promise is we can build several observables which are sensitive to this divergence. Observables which, if you have many of them and they are uncorrelated, you could naively think that you can get better constraints than simply the scale-dependent bias. Is like having many scale-dependent biases, naively. But also, you can expect to have different systematics and maybe break degeneracies. And another advantage that these methods potentially have is that the squeeze limit is very easy to model. So it's very easy to model also the covariance and it's also very easy to model relativistic effects. So, let's look at the squeeze limit methods. So the squeeze limit, as I said, is when one momenta is much smaller than the other two. In these few slides, I will call this small momentum Q. Small momentum means large wavelength. So these methods focus on the following physics. The squeeze limit has information about how a large wavelength fluctuation modulates short wavelength physics. A correlation function in the squeeze limit, an n+1 correlation function in the squeeze limit, can be seen as the correlation between the large wavelength fluctuation with the short wavelength endpoint function in the presence of that low wavelength fluctuation. In particular, if we observe a correlation between the two-point function and the gravitational potential, then we will have observed local non-Gaussianity or multifield inflation. That's because of course, if we don't have primordial non-Gaussianity, the gravitational potential cannot have any effect on short wavelength physics. In particular, it cannot have any effect on the two-point functions. And the promise of this method is also that it can be, since it's based on this very simple argument, this argument holds no matter, you don't have to model the endpoint function here, you only have to model how it responds to a long wavelength fluctuation. So in principle, it can be pushed to very short wavelengths, so to very small scale modes, because this argument doesn't depend on the modeling of these short wavelength modes. If you observe it, you can focus on trying to detect the 1/q² behavior. To understand this a bit better, let me use a parameterization that we introduced in this paper here. So we do it at the field level. So consider how dark matter density contrast field responds to the presence of a long wavelength gravitational potential. So, of course, at zeroth order, and we will assume that the long wavelength gravitational potential is small, and also that the density velocity related to this potential is small because it's long wavelength. So we'll assume that the linear approximation holds. So we will go linear in this long wavelength mode, and we will also do an expansion in derivatives because it's a long wavelength mode. Derivatives are suppressed. So of course, at zeroth order in the long wavelength mode, we get this. At first order, in the absence of primordial non-Gaussianity, we can include a few more terms. This term is guaranteed by the equivalence principle. This term is trivial in the sense that it's simply given by the fact that your density field, the one that you observe in the sky, you observe it in your reference frame. This kind of correlation appears if you go to a reference frame co-moving with this short wavelength mode. This term would disappear. So it's a trivial effect which has no dynamics, simply due to a change of reference frame, while these terms encode the dynamical response. And these terms have two derivatives of the gravitational potential. Remember that the density contrast is the Laplacian through Poisson's equation of the gravitational potential. So here we have the Laplacian, and here other second derivatives. We can choose to subtract the Laplacian, but for simplicity I don't do it here. So these are just other second derivatives contained here. And these contain the dynamical response. I write capital deltas, which are the small wavelength part of this expression, simply factorizing the long wavelength mode. There should be an L here. This is the long wavelength mode. Because the deltas are not necessarily the same as the density contrast. They, in principle, would have to be computative if you want to model, if you want to an explicit model, which, however, we don't need. And if you have local non-Gaussianity, you would add a term like this. So your gravitational potential at zeroth order derivatives would appear in this expression. In the absence of local non-Gaussianity, the equivalence principle guarantees that this term should not be there. The advantage of these methods, as I already said, it's simple covariance, is that covariance, as you can see, modeling this is very simple because you can focus on the long mode, which has a simple effect on the short modes. And this simplicity extends to the covariance. And in principle, the short wavelength modes can be pushed to nonlinear scales because you can focus on trying to detect the 1 over q squared without caring what these functions of k are. And I will show you a couple of ways to do this. And it can also have complementary information with respect to the scale-dependent bias. So one way to try to measure this squeeze limit, apart from the scale-dependent bias, which as far as I know was first introduced in this paper here, is by computing, is by using the power spectrum itself as some new observable. So you can imagine computing averaging the power spectrum over, or using averages on a small region to define your power spectrum. So you have your local, say, power spectrum, which lives on top of a long wavelength mode. So if you plug this expression into the 2-point function, you get this expression for the power spectrum. So you see that there will be, in the presence of primordial non-Gaussianity, the power spectrum will be modulated by the long wavelength mode. The power spectrum computed using small scales will be modulated by the long wavelength mode. It will be larger, for example, here than here, than here. And this 1 over q squared modulation, you can try to look for this 1 over q squared modulation. This was tested in Quixote simulations by this group here. And they find that using the matter field, this is much more powerful than the scale-dependent bias. But due to shot noise, it becomes comparable with the scale-dependent bias, at least for the halo density of the Quixote simulations. And they use this range of scales here. In spite of that, I still think it's an interesting method because due to all the what I said before, that it's easier to model the covariance than, say, using the bispectrum. So if you hope to use the bispectrum to break the generalities, you can use this instead. It's also very easy to model this modulated power spectrum. It's not as complicated as the bispectrum itself, so it's easier to produce a model for this. And I also think this method hasn't been exploited to its fullest potential. Another way to do to use this is to look at the bispectrum, the galaxy bispectrum itself. So let's talk about the halo bispectrum or the matter bispectrum. And if I plug this expansion, in the bispectrum, I get this. Here's the primordial non-Gaussianity, here's the equivalence principle term, and the response function terms, the responses to a long wavelength fluctuation. So the problem here is that, of course, you would have to model the responses, but you can get around that if you average over the short wavelength mode. So if you average over K1, you get something which depends only on Q. You don't know what this dependence on Q is, but you know for sure that if you detect a 1 over Q squared behavior, it's primordial non-Gaussianity. So you can try to measure these coefficients, and then you can use the simplicity of the squeeze limit or simulations to relate this coefficient with FNL. In the second paper, they related using the simplicity of analyzing the squeeze limit related to FNL, and you can have additional constraints. What they find is that they find constraints which are not a substantial improvement over scale-dependent bias, though they are a bit worse than the previous work I mentioned. which however for simulations came later than this one. And but still, this method again is interesting because the squeeze limit is very easy to model. It has a very simple covariance, and something that we've been ignoring up to now is that it's very easy to model the relativistic effects on this observable. If you want to model relativistic effects on the full bispectrum, it's messy, to say the least. You have to go to, if you want tree level, you have to go to second order perturbation theory, which in GR is quite cumbersome. While here, you can use this argument of the long wavelength mode modulating short wavelength physics to very easily compute relativistic effects on this kind of observables. So it's much simpler to model than the bispectrum, and it can be combined with the scale-dependent bias to break degeneracies, etc. So I think it still has power. In particular, I think I personally think it hasn't been exploited to its fullest, because I think that one can model the response functions, these response coefficients. It's possible to model them phenomenologically. One expects them from measurements of response functions that are in the literature. One expects them to have a simple shape. And in this work here, we did that. So without primordial non-Gaussianity, just using this the model that I showed at the beginning, we model the response functions as simple polynomials for dark matter. And we are able to model the bispectrum to very small scales for the short modes. And we are able to model it with a few percent error, but the percentage error is actually not as important as the fact that this is the number of sigmas that we are away from the simulation. So you can see that within 1 sigma, our model fitting for these 6 coefficients, within 1 sigma, we can model the squeezed bispectrum where the short modes are on very nonlinear scales. So the short modes up to 0.7. And since we can model these response functions, I think there is still some work to do to bring these squeeze limit methods to their full potential. Moreover, the squeeze limit methods, to be honest, current surveys are not designed for this kind of methods, because they were thought for the more traditional methods, and in particular, we can greatly increase the power of these squeeze limit methods according to the analysis of De Putter and the other group that you studied the modulated power spectrum. We can improve this by having a smaller shot noise. So, yeah. Another alternative method is using topological data analysis. The idea is that your galaxy distribution is a point cloud. This point cloud has topological features that roughly correspond to the objects of your large-scale structure. And we already know from work that many people have been doing in the last few decades that numbers of objects in the large-scale structure are very sensitive to non-Gaussianity. But it has been very hard to exploit this fact to its fullest potential for constraining non-Gaussianity, because defining, for example, number of voids is difficult, or using small number statistics to constrain number of rare halos is extremely hard. So this using topological techniques promises to be a more systematic way of doing that. The topological features we use are called persistent homology. So homology counts clusters, loops, and voids. It does it by starting from a simplical complex. A simplical complex is basically you put simplexes together in such a way that It's complete in a sense. So a simplex in 3 dimensions, a simplex is like a triangle. In n dimensions, in 3 dimensions, we have the following simplexes. There is the 0 simplex, which is just a point, the 1 simplex, a line, the 2 simplex, a triangle joining 3 points, and then you have a tetrahedron. And in 3 dimensions, you have 3 homology groups. Homology groups are simplical complexes with non-trivial topologies. You have clusters, which are just a bunch of points all joined together. You have H0, which are just a bunch of points joined together, which for us, they're like having clusters of points. You have H1, which are loops, meaning circles in 2 dimensions, empty circles. So lines without being filled in by triangles. They cannot be deformed trivially to a point, and they're kind of loops in your filaments of the large-scale structure. And finally, H2, which are regions delimited by triangles, which are not filled in by tetrahedra. So you cannot deform them continuously to a point, and they would correspond to voids in the large-scale structure. So we can build simplical complexes, and in this way count systematically without even having to define them, cluster loops and voids. But how do you build these simplical complexes? A way to do it is by defining some scale. So you have your point cloud and you define a scale. And with that scale, you draw a sphere around each point. And when the spheres cross, when 2 spheres cross, you put a line. When 3 spheres cross, you put a triangle. When 4 spheres cross, you put a tetrahedron. Now, of course, doing it in this way is very noisy and depends very much on the radius of the spheres. So, but what you can do is keep track of all the structures you form at each value of your scale. So as I increase the scale, and you can, in particular, keeping track is very easy because you can see that as I increase the scale, some features are born and some features die. So let's take a look. There are no features here. There are just a few separated clusters. As I increase the radius, these 3 points are joined together. So we have a bigger cluster. I increase the scale a bit more, and we form a loop here. This is a non-field. This is a non-field loop. So we say that at this scale, this loop is born. But if I increase the scale, this is filled by a tetrahedron, and this feature has died. And we can keep track of each feature, at which scale it's born, and at which scale it dies. And this has all the information of the topology. And it's a systematic way of keeping track of structures. However, this doing it in this naive way is very sensitive to outliers. So if you have something in a vacuum, so if you have a single halo in a vacuum, it can ruin your void. If you have a single halo on a void, it can ruin your void at a scale much larger than you expect. So to make it more robust against outliers, these people here were found a smart way to define the scaling such that for isolated points, the scaling is suppressed. I can give you more details during the discussion. So each feature will have a birth and a death, and you can plot the birth against the persistence, which is the death minus the birth, or how long it lives. And you can see that it has an effect on non-Gaussianity. So here is for local non-Gaussianity of 250 minus a Gaussian simulation. This is equilateral non-Gaussianity of 1000 minus a Gaussian simulation. And you can see that it has an effect on the structures. We also learn that the characteristic scales of these features is a few tens of megaparsecs. So it's a very different scale from those probed by correlation functions. So it can be potentially a complementary probe to standard methods. And we want to figure out, so you can see that it has an effect. We want to figure out how powerful this method can be. We do a simple Fisher matrix analysis, which is not optimized because this filtration has some hyperparameters which we don't optimize. And we also, in order to choose the data vectors, we do it basically by hand. We have no optimal way of extracting information from this point cloud of death versus birth. And by hand, we choose the birth and deaths of 0, 1, and 2 dimensional topological features. And for each one, we do a histogram with just 5 bins. We choose the number of bins just that we can compute the covariance because we don't have that many realizations, but also we want each bin to be Gaussian distributed so that we can apply the Fisher analysis. If we have very few bins, some bins will be noisy and non-Gaussian distributed. And we apply the Fisher analysis, meaning we compute the derivatives of these data vectors with respect to FNL. And these are our results, where we also model spectroscopic errors and photometric errors. And we learn that types of equilateral and local non-Gaussianity are not completely degenerate, they are not degenerate, and the spectroscopic and photometric errors don't affect the constraints by orders of magnitude. This constraint is obtained with a volume of roughly 1 gigaparsec cubed. And for the equilateral non-Gaussianity, they are much better than the constraints that you would obtain from the standard methods with such a volume. So even if this is highly unoptimized, we already see some improvement over the standard methods, but there's still a lot of work to do because there are many open questions in the direction that I can tell you during the discussion. So in conclusion, it's hard to get errors on the FNL equilateral of order 1 with standard techniques. This opens the need to explore alternative techniques because FNL equilateral of order 1 has phenomenological interest. The scale-dependent bias is still the most promising tool for local primordial non-Gaussianity, and you can combine it with the bispectrum to break degeneracies. However, the squeeze limit techniques could be refined to fulfill the promise of giving many scale-dependent biases. And even in the pessimistic scenario, that they are not a big improvement over scale-dependent bias, still they are much easier to model than the bispectrum. So if you want to break degeneracies, maybe you should think of using these techniques rather than the standard bispectrum because the covariance is simpler, the model is simpler, you can push it to smaller scales, and relativistic effects are much simpler to model than for the bispectrum. And finally, persistent homology techniques can be used to greatly improve limits on equilateral primordial non-Gaussianity. We haven't optimized, for example, the observables that you can look at, but that still needs a lot of work. That's it. Thank you.